Good afternoon, everyone. Today, I will present our machine learning solution designed to support credit card approval decisions while following responsible AI principles. The objective of this project is to develop a predictive model that can help financial institutions evaluate credit card applications more efficiently, while ensuring that the decision-making process remains transparent, explainable, and fair. In addition to model performance, we focus on three responsible AI components. First, fairness evaluation across demographic groups. Second, model interpretability, so decision maker can understand why the model makes certain predictions. And third, transparency in the model process to support regulatory compliance and responsible development. In this presentation, I will walk through the data explanation process, model development and evaluation, fairness analysis, and model explainability. Next, let's see the dataset overview. We begin with exploratory data analysis to understand the structure of this dataset. The dataset contains demographic and financial information about credit card applications, include age, income, employment history, family size, and housing characteristics. The target variable indicates whether a credit card application should be approved. As we can see from this distribution, the dataset is imbalanced. There are approximately 8,400 negative cases and about 1,300 positive approvals. This means the approval rate is roughly around 13 to 15%. Because of this imbalance, accuracy alone would not be a reliable performance metric. Therefore, we also evaluate the model using precision recall, F1 score, and rocket UC. These metrics provide a more balanced view of model performance, especially when predicting the minority approval case clause. Next, we explain the distribution of applicant characteristics. This figure shows the age distribution of applicants. Most applicants fall between the ages of approximately 25 to 60, with the peak around the late 30s and the early 40s. This suggests that the majority of credit applications are working ages individuals with potentially stable income sources. Understanding these demographic patterns help ensure that our model is trained on representative population characteristics. We also examined how income relates to approval outcomes. This chart shows the income distribution for approved and non-approved applications. Interestingly, we observe that the income distribution for both groups are relatively similar, although approved applicants tend to have a slightly higher median income. This suggests that income alone is not the sole driver of approval decision. Instead, multiple features such as employment stability, family characteristics, and account history contribute to the final decision. We evaluated three different classification models: logistic regression, random forest, and light GBM. While random forest and light GBM achieve higher accuracy, this was largely due to prediction the majority clause. For example, random forest achieved nearly 80% accuracy but had a recall of only about 0.11 for approved applications. This means it failed to correctly identify most of the accurate approvals. In contrast, logistic regression achieved a recall of approximately 0.52. This means it correctly identified more than half of the true approval cases, though its accuracy is lower. It performed better in identifying the minority clause, which is critical in credit approval scenarios. Additionally, Logistic regression provides strong interpretability through model coefficient. For this reason, we select logistic regression as our final model. Next, we evaluate the performance of the final model on the test dataset. For the negative class, the model achieves a presence of 0.88 and a recall of 0.56. For the approval class, the model achieves a recall of approximately 0.49. This means the model successfully identified about half of the true approval cases, where the presence for approval is lower at around 0.15. This reflects the conservative nature of approval predictions. The overall ROC AUC score is approximately 0.55. Although the predictive power is moderate, the model provides interpretable decision logic and balanced performance across metrics. In financial institutions, transparency and fairness are often just as important as real predictive accuracy. We also analyze the learning curve of the model. The training score starts higher and gradually decreases as the training set increases. Meanwhile, the validation score steadily increases and eventually stable. This pattern indicates that the model is not severely overfitted. Instead, the model demonstrated reasonable generalization performance as more data is introduced. This suggests that the model has reached a stable balance between bias and variance. To ensure responsible development, we evaluate fairness across gender groups. The approval rate for gender group 0 is approximately 38.7%, while the approval rate of gender group 1 is about 55.9%. We also examine the model accuracy across this group. Accuracy for group 0 is around 0.6, while accuracy for group 1 is about 0.46. These differences indicate that the model behaves differently across demographic groups. While this doesn't necessarily imply unfair bias, it highlights the importance of monitoring fairness metrics during model development. Financial institutions must continuously evaluate these metrics to ensure compliance with regulatory requirements and ethical AI standards. To improve model transparency, we analyze the global feature importance derived from logistic regression coefficients. The strongest positive driver of approval include account length, family size, and certain categorical housing feature. For example, the coefficient for account length is approximately 0.3, indicating that applicants with longer account history are more likely to receive approval. Family size also show a positive influence, suggesting that the stable household structures may correlate with credit reliability. These insights help financial analysts understand which factors contribute most strongly to approval decisions. Finally, we generated a local explanation for an individual applicant. For this example, the largest positive contribution include unemployment strategy status with a contribute of approximately 0.29, with a contribute of 0.26, and family size with a contribute of 0.26. This factor increase the probability of approval for this applicant. On the other hand, negative contributors include account length and certain categorical housing features. This local explanation provides transparency into how the model evaluates individual applicants. Such explanations are critical for regulatory compliance, as financial institutions must be able to justify automated decisions affecting customers. In conclusion, this project demonstrates how machine learning model can support credit approval decisions while adhere to responsible AI principle. We developed and evaluated multiple models and selected logistic regression for its balance of performance and interpretability. We assess fairness across demographic groups and implements both global and local explanation methods to improve transparency. Together, these techniques help ensure that automated decision systems remain accountable, explainable, and aligned with regulatory explanation. Thank you for your time.